All right, so let's get started then. Today we will continue to finish off the things that we didn't finish on Friday. That has to do with Nyquist pulses and intersymbol interference, and then go on to talk a little bit about receivers for pulse amplitude modulation. So, but a short review of what we did last week. We talked about pulse amplitude modulation, okay? And that's a workhorse in communications. This is a standard way to compute this transmitted signal from bits. So the idea is that we take some bits, a block of bits, and then we represent that as a amplitude or a symbol. Symbol and amplitude means the same thing in this context. And these amplitudes then are multiplied with pulse shapes G and then form the transmitted signal. So the transmitted signal consists of delayed versions of the pulse multiplied with the corresponding amplitude. Okay. This mapper here, the only purpose of this mapper is to take some bits and represent that with an amplitude. So if we want to take capital K bits, then we need capital M 2 to the power of K possible amplitudes. And then the mapper is just a table where we list all the bit patterns and how they map onto the corresponding amplitudes. Okay, and we will talk later on how to choose these amplitudes, and a little bit later on what this mapping, the importance of that. So for the time being, we just assume that we have some type of mapping here. Okay, so we have a bit stream coming in here, which is converted to a stream of amplitudes. And each of these amplitudes are then multiplied individually with delayed versions of the basic pulse to form the transmitted signal. So if we talk a little bit about rates here, how fast are we transmitting information, then this capital T here, sometimes it's explicit in this block as we printed here. In the book it's not explicit, but it's understood that we transmit one pulse every t seconds. So if we transmit one pulse every t seconds, then we transmit one amplitude or one symbol every t seconds. So the symbol rate, capital R subscript S for symbol, is 1 over t. Okay. We transmit one symbol every t seconds. Now each symbol here carries a number of bits, k bits. Or if we want to solve this equation, we see that k is the log 2 of m. So each symbol transmits a number of bits. So the bit rate is related to the symbol rate by a multiplication of log 2 of m. Okay. So typically the bit rate, the number of bits we transmit per second, is larger than the number of symbols we transmit per second, simply because one symbol carries multiple bits. Okay. Now it could be that each symbol carries exactly one bit, then it's the same, right? Yeah. Exactly. Okay, so then I think, okay, this curly A or calligraphic A here is the set of all of these amplitudes, A1 through AM, the ones that we use in the mapper here. And this is called the symbol alphabet, and we'll see the importance of that a little bit later. Okay, questions on this? No, okay. We will see later on that we will often filter pulse amplitude modulated processes, and if we do that, we got another PAM process. So if we have some amplitudes, AK, a sequence of AKs coming in here, each of these AKs multiply a delayed version of the basic pulse shape, and then we feed that through a linear time invariant filter with impulse response f of t. The output we get then is a pulse amplitude modulated process with the same amplitudes. So AK here is the same as we had in the input, and it's multiplied then with delayed versions of a pulse, H. And this pulse H is the convolution of the basic pulse of the first PAM convolved with the impulse response. So it's not difficult to prove this. So whatever is in this, this square here or rectangle can be illustrated with the new PAM process with the same input, but the only change is that we have changed the basic pulse H here from G to H. the pulse rate or the time between pulses remain the same. Okay, so this will be useful a little bit later, as we will see. Okay, so, and here we see it actually. So a common receiver for pulse amplitude modulation looks something like this. Okay, so again we have some symbols here which carries data. Pulse amplitude modulator forms the transmitted signal S. It goes over the channel, and typically the channel adds some noise to this. So that is what destroys our ability to communicate. So the receive signal is the transmitted signal plus noise. Okay, and the first thing that happens in, I would say, any receiver is that we filter the receive signal. And basically we do that in order to suppress noise. Okay. So this filter F here is important that we select that properly. By selecting it, I mean we select the impulse response of this filter in a smart way. So anyways, if we have this impulse response F here, then we have some output Y, and this we sample, and we sample that with the same rate as which we transmit symbols. Okay, so we sample this once per symbol, and then we get some discrete sequence YK here. So again, K here is some type of time index. And this K corresponds to this K. So in the best of worlds here, Y of K here would be equal to A of K, or at least close to it. That's what we're aiming for. In the noise-free case here, we really would like to produce, make YK equal to AK. Okay, so let's look at the noiseless case here. So essentially what we do here is we forget about the noise for the time being, and just look at what is then Y here. Well, we know that this will be then a pulse amplitude modulated process where the basic pulse is the convolution between G and F, and let's call that H. So H here is the convolution between G and F, and then we would like to take samples of that signal. So Y of T here, we would like to take samples of that, and we take one sample every T seconds. And then it's easy to show that Y of K is then equal to AK, the thing that we're looking for, multiplied with a constant, which is the amplitude of the pulse H at time 0. So as long as this is not 0, that's fine. If it's 0, it's bad, but let's assume it's not 0. So let's assume that this term is non-zero. Then we can figure out AK if we know H, right, from this term. And then we get something else, this intersymbol interference. And what is that? Well, it's a sum, infinite sum, over these symbols that we will decode a little bit later, but we're not interested in them right now. So these AMs here are symbols that eventually will be decoded, but we're interested in the kth one now, not the mth. We see that m here is not equal to k. So this is some other symbol that we don't necessarily care about right now. And then it's multiplied with samples of the H function, the H signal here. So this is interference term. It's a term which interferes with us in our ability to figure out AK. And since it's due to other symbols, it's called intersymbol interference. Okay. So ideally, we would like this to become 0. Okay, because if it does, if this whole thing disappears, then basically we can figure out what the transmitted symbol was by just dividing Y with H0. Okay? So how can we make this 0? Well, we have two terms, or two factors here. We have the symbols, and then we have the samples of H. The symbols will be non-zero. Okay, so eventually we would like to decode these, so it's not wise to put them to 0, right? So the only thing we can do then is to hope that the samples of H become 0. If they do, then this product becomes 0, and then sum of zeros becomes 0, okay, and everything disappears. We showed Friday that if we have a pulse G, which has support, or think of this as duration, which is less than t seconds, then we will have ISI-free transmission if F also has support which is less than t. Okay. So one simple example of this would be G, which has some extent, t. It doesn't matter what the shape is, but it's something. And then we can pick h to something which is also time limited to t, and it really doesn't matter how it looks like, something like this, for instance. This is not a very good choice at all, okay? But at least it will not give you inter-symbol interference. Okay. So what's wrong with just doing this, having pulses which are time limited to t seconds? Any guess? If I say it has something to do with the bandwidth of the transmitted signal, so the bandwidth of S here, what could be the drawback of having time limited pulses here? Yes?
You get a very large frequency band.
Yes, exactly. So very good. So what we get here is something, a signal which occupies a large frequency band. And as we will see later on, this is one of the precious resources in communications. There are two basic resources: power of the transmitted signal, bandwidth of the transmitted signal. Okay? So these two things are good things in the same, that they will increase our ability to communicate. However, bandwidth is limited on the medium that we have. Okay? So there is a certain bandwidth of this cable. There is a certain bandwidth of a radio channel, and we want to use that as efficiently as possible. So if we're interested in having band-limited transmissions, okay, where these the spectral content of the transmitted signal here is confined to a relatively small bandwidth, then the only thing we can do then is to choose pulses which are wide. Okay? And if they're wide, we have to transmit very slowly, or we need to make the pulses overlap. Okay. So now what we will see that there is a way to select pulses which overlap but still do not produce inter-symbol interference. Okay. So bandwidth. What do we mean by bandwidth? The first thing I would like to stress here is that there are many definitions of bandwidth. Okay. And the reason for this is that they are useful in different contexts. Okay. What we are talking about now is signal bandwidth, and this should not be confused with which is common in the books that you read in this class and other classes, which has to do a little bit more about protocols and so forth, because then bandwidth is typically measured in bits per second. It has to do with data rate. Okay. So, but now we're talking about signal bandwidth in hertz, and this should not be confused with data rate, which is measured in bits per second. Okay. So when I talk now, and I talk about bandwidth, I mean hertz, okay? The frequency content of the transmitted signal, for instance. Okay. Now, suppose then we look at the basic pulse G. It has a spectrum, that is the Fourier transform of G is this integral here. I'm sure you've seen it before. The absolute bandwidth is defined as the difference between the highest and lowest positive frequency content in G. Okay, so what do we mean by that? Well, if we plot the magnitude of G, okay, first of all, why do we want to plot the magnitude here? Well, because typically the Fourier transform is a complex function. Okay, J here is the square root of -1, for instance. So in general, G here is complex. Okay, so if we want to say something about its content, we can plot the real or imaginary parts of it, or we could just plot the absolute value of it. Okay, suppose we plot the absolute value of this, and we get something that looks like this. Then the bandwidth of that is W. Okay, it's the difference between the highest frequency content and the lowest frequency content, and lowest positive frequency component. Okay, so we don't count this to the left here. The smallest it can be is 0. Okay, so this is the bandwidth, and sometimes you see books where bandwidth is maybe from here to here, so it's more like the double-sided bandwidth. But we will talk about the single-sided bandwidth like this, because then everything works with our equations. If you look in another book and you see other equations, and they don't match what we talk about today, could mean two things: either that I did an error, or that the bandwidth has another definition in that book. I don't know which one is most likely, but you know, either of the two are the possibility. Okay, so bandwidth then, when we have these are called baseband signals, where the power or the energy content of G is located around 0 hertz. But we also use passband signals mainly when it comes to radio frequencies and things like that, radio transmission. Then we put the energy of the transmitted pulse at some higher frequency. Then the bandwidth is the smallest positive frequency, which is this one. Sorry, the highest positive frequency, which is this one, and the smallest positive frequency, which is this. And the difference between that is the bandwidth in this case. Okay, questions? Okay. So now we have now a notion of bandwidth, and what we would like to do is to choose a pulse G. Which pulse? Oops, sorry. We would like to choose this pulse G to have a compact spectrum. Okay. And the reason for that is that then we can transmit another channel to the right of it, and another channel, and so forth, right? Looking a little bit ahead. Okay, so we have the same setup as before here. So now it's also bits to symbols are explicitly mentioned here. But bits to symbols to transmitted signal, receipt signal is the transmitted signal plus noise, filter, sample, and then we get Y again here. Now, suppose G has bandwidth W, so it's now band limited, which means that it cannot be time limited. Something which is band limited cannot be time limited. Something which is time limited cannot be band limited. That's an unfortunate fact of life. Okay. It would be nice if we can have something which is both time limited, band limited. We cannot. Okay. According to the bandwidth definition that we use here. Okay, but suppose it has a bandwidth W. We have selected G here to have certain bandwidth. Then the question we ask ourselves, when can we have inter-symbol interference-free transmission? And the following result that we will show soon follows. It has actually to do with the symbol rate. Okay, so what is the symbol rate? The symbol rate, RS, is which variable here, now a little bit, which variable here determines RS, the symbol rate? Is it B, A, S, N, T, G, R, F, T, Y? What is it?
1 over T.
1 over T, very good. Okay, so symbol rate is 1 over T. Okay, so the RS is the speed, how often do we send symbols, essentially? And you can imagine that we would like to transmit a lot of data per second, which implies that we can do that if we do transmit a lot of symbols per second. Okay, so we want RS to be large. However, if the symbol rate is greater than twice the bandwidth, it is the unfortunate fact that inter-symbol interference-free transmission is not possible. Okay, so if the symbol rate RS is too large in comparison with the bandwidth, we have to accept that Y of K here will contain inter-symbol interference. Too bad. This is not what we want typically. However, if we reduce the symbol rate to be exactly equal twice the bandwidth, then it's actually possible to have inter-symbol interference-free transmission, but only with a very particular choice of G and F. Okay? If and only if G convolved with F is a sinc function. You remember what the sinc function is, right? It's sinc of x is sine pi x divided by pi x. Okay, so that's the sinc function. Okay, so we just have to choose G and F and convolve them and hope it's a sinc. If it's a sinc, then we're fine. It has to be sinc T over capital T, and T here again is this T between the time between pulses. All right, if the symbol rate is less than twice the bandwidth, then it's still possible to do intersymbol interference-free transmission, and then there are many choices for this that produces intersymbol interference-free transmission. Okay, so then we have some design freedom. Okay. So we're going to show why this is the case momentarily. But again, I would like to stress the fact that if we have G which has a duration or support less than T, and therefore infinite bandwidth, and F also has support less than T, then we have intersymbol interference-free transmission. So what's inside the red box here is only applicable when G has a finite bandwidth W. Okay, which is what we would like it to have. Okay, so in order to prove this, we need to take a little bit of a detour into the sampling theorem. And this is something that I assume that you've seen before, but perhaps not with this notation. So I will just briefly introduce this a little bit. If you think that this is strange, then please review your favorite book in signals and system theory to figure out why this works. Okay. So the sampling theorem is quite amazing, actually. So it says basically that if we have something which is band limited, a signal, a continuous signal, we can actually completely specify that by its samples if we sample fast enough. Okay, with zero error. Okay, we can always approximate, right? But with zero error. So suppose we sample a continuous time signal h, and we sample that every t seconds. Then we get a discrete signal hd for discrete, and square brackets here to indicate that it's also a discrete signal. So n here is an integer. And it's just simply the corresponding samples of the continuous type signal h at every t seconds. Okay, so here we have a continuous signal, here we have a discrete signal, and they're related through sampling. If we take the Fourier transform of h, we get capital H. If we take the Fourier transform of hd, we get capital HD. Okay, so this is the discrete time Fourier transform. And this is the continuous time Fourier transform. Okay, so the Fourier transform are related then as follows. So the continuous time Fourier transform of h, this curly f of h, which is this integral here, it's just the definition of the Fourier transform, is related to the Fourier transform of the discrete signal, which is denoted like this, which is this sum, right? There are no integrals for discrete signals, and yeah, well, there doesn't mean, well, essentially this integral is a sum. It's just gone into some type of limit, right? But anyway, so there is a difference here. And also to keep things separated here, we have the frequency variable small f here and the discrete frequency variable capital F here. Anyways, the interesting part here is that if we relate h and hd through sampling, then the discrete time Fourier transform is related to the continuous time Fourier transform through this formula here. Okay. So, and what is amazing about this is that, well, it's truly amazing, by the way, let's not go down that path right now. But anyway, so we have here, the sampling theorem just tells us that the discrete time Fourier transform is related to the continuous time Fourier transform according to this formula here. And basically we see just that we have different versions of h translated according to the over the frequency axis here, and we sum all of them together and divide by 1/t. Okay. So that's the sampling theorem. Any questions or comments about that? Is this familiar to you? Somewhat? Okay. Right. Now, let's get to the heart of the thing here. So we will talk about Nyquist pulses. And Nyquist pulses are such pulses which are band limited, which produces, which gives no intersymbol interference. Okay. So Nyquist comes from this guy, Harry Nyquist, actually. So it's a Swedish dude from Värmland. So Värmland's big contribution to signal theory, perhaps. But he spent all his work life in the United States. So we'll just call him Nyquist for that reason. Anyways, a Nyquist pulse is a pulse when you take samples of it every t seconds, that only one sample is non-zero, namely that one which is at the origin when n is equal to 0. All other samples are non-zero. So this is a time domain requirement. The corresponding requirement of the Fourier transform of h is this. So we take the Fourier transform of small h and we get capital H, and then we form this sum and divide by t, we get that to be equal to 1. So these two conditions are equivalent. Okay, and again, capital H is the Fourier transform of small h, which is this integral. And so let's see why this is true. And the proof is actually not very difficult. So essentially what we want to do is to show that this implies this. And we will use the sampling theorem to do that. And then we know it goes the other way around also. Okay, so let's do that. So if we have, what we really want to do is we would like to avoid ISI. Okay, and this means that the discrete time version of h, which is the continuous time signal sampled every t seconds, that should be equal to 1 when n is equal to 0 and 0 otherwise. Okay. So essentially what we're looking for is a pulse where we have 0 crossings every capital T seconds. T, 2t, 3t, and also negative t, negative 2t, and so forth. And anything we can draw, and we need one more thing, we need it to be 1 when t is equal to 0. Okay, so any pulse we can draw through these circles is a Nyquist pulse that will produce 0 intersymbol interference. Okay, so it could be, you know, maybe something, something of this nature. This would do it. Right? There are many different pulses. Okay, but anyways, so this is the condition. So how can we figure out what this means in terms of the Fourier transform of the continuous time signal here? Well, then we use the sampling theorem, and the sampling theorem tells us so the sampling theorem tells us that the discrete time Fourier transform of HD, which is the sum from, this is just the definition of the Fourier transform, sum from n from minus infinity to infinity, HD of n, e to the power of negative j 2 pi capital F n, like this. Okay. So it's just the definition of the discrete time Fourier transform. What is this equal to for HD in this case? So HD is a discrete signal which is non-zero at one point when n is equal to 0, and is 0 for all other points. So if you look at the product here, only one term is non-zero, namely the one when n is equal to 0. So when n is equal to 0, hd is equal to 1. What is this equal to? The complex exponential here. When n is equal to 0.
It's just 1.
1, exactly. So we get 1 times 1, and last time I checked, it was equal to 1. Great, that was simple. Now, the sampling theorem tells us that the Fourier transform of the discrete signal is related to the Fourier transform of the continuous signal through this sum, right, that we saw earlier. So this should be equal then to 1 over t sum k from minus infinity to infinity, capital H, which is the Fourier transform of the continuous signal, evaluated at capital F minus k divided by capital T, like this. Okay, so this is just the sampling theorem. Okay, now we change variables. And set small f equal to large F, capital F divided by T. And then the formula becomes, and then we do this substitution. We do this substitution in the left-hand side and the right-hand side of this equation. Just change variables. We're allowed to do that. So we have one function to the left, which is a function of f. It's a very simple function of f. It's just a constant function. So it doesn't change. But in the right-hand side, we just change capital F divided by T and replace that with small f. So the final formula we get is 1 equal to 1 over T sum k from minus infinity to infinity, capital H, F minus k over capital T, like this. Okay, so this condition inside blue here is equal to this condition up here. These are equivalent. So we can either specify something in the time domain, or we can specify something in the frequency domain. So when we're looking for h, we can either use the frequency domain representation for it, or its time domain expression for it. And it actually turns out that it's simpler to work with the frequency domain. It's not obvious from this, but we will see in a second that that is the case. So any questions on this derivation? No? Okay. So what we have done now is to prove this relationship. Right? We just did that. And it was a simple application of the sampling theorem. Okay. Now, since t here is related to the symbol rate, we can write this also as a sum where we, instead of having t, we insert the symbol rate rs. So 1 over t here is 1 over, or we can multiply t over to this side, and then we get t here, which is 1 over the symbol rate, and we can replace 1 over t here with the symbol rate. So it's the, so this is the same what's on top here, right? Okay. So let's see what we can deduce from this formula. So this formula, how can we use that in order to justify what's inside the red box here? Okay. Can we relate symbol rate and bandwidth and say something about what h should be, the convolution of g and f? Okay, so let's start with something here. Let's start with g. We pick a pulse, g, which is band limited to w. So your favorite band limited pulse. Let's take that. What does it mean? It means that the Fourier transform of g is 0 for all f greater than w. Okay, so I don't know if we would plot g of f here. We know that it's 0 outside plus and minus w. And then it's something in between. I don't know. Something like that. Probably not that. But anyways, right? So we just pick something which is band limited to w hertz. Okay. Then what can we say about h? Well, h is the convolution between g and f. Okay, so can we say something about the band limitation of h? Well, let's take the Fourier transform on the left-hand side and right-hand side of this, and then we get capital H, the Fourier transform of small h, and then the product of the Fourier transform of g and the product and the Fourier transform of f. So it's a little bit unfortunate here that it's capital F and small f and so forth. But okay, I'm sure you understand that there is a difference between this f and this f. Anyways, so we have here that h of f is g times capital F. And since g is 0 outside the frequency range from negative w to w, then so must h be. Okay, so h is also band limited to the same bandwidth as g. Okay. Why is this important? Well, if we want to check if we can get intersymbol interference-free transmission, what do we need to do then? Well, if we're working in the frequency domain, we can take the frequency domain part of the Nyquist criterion, which means that if we take the sum of these h functions and then add them together, they should be 1 over rs. Okay? So we plot something as a function of f, and we hope that the sum of all of these terms becomes a constant function. That's what we're aiming for. If that is the case, then we have intersymbol interference-free transmission. So let's put in h here. I don't know what h looks like, but maybe it's something like this. For sure, it's band limited to w hertz. Okay, so this is the first, or when putting in k equal to 0, then this is the term that we get. When we put in k equals 1, we get this term. When we put in k negative 1, we get this term. Okay, so all of these pulses we get, they go as far as you can go to the left, to the right, and as far as you can go to the left, right? And then we add them together. Does this give us intersymbol interference-free transmission in this case? If we add these triangles, do we get a constant function? No, we don't, right? I mean, we get 0 here, so we get essentially this thing here. So this will never give intersymbol interference-free transmission. As a matter of fact, as long as there is a gap here between this pulse and this pulse, we're screwed. There is no way we can make this, add these pulses together and get the constant function, right? Because whatever it is inside here, it would drop down to 0 when there is a gap and then go up and be something, right? So we need the gap to close in order to have a chance for intersymbol interference-free transmission. And what is the gap? Well, it's the difference between this point, and this point is the symbol rate minus w, so it's rs minus w here, and it's w here. So the gap is, the length of the gap is rs minus 2w. Right? rs minus w, so rs minus 2w. Okay, so now we can start to do things. So if the gap is greater than 0, that means that rs minus 2w is greater than 0, which is that rs is greater than 2w. Then h can never be Nyquist. So, sorry, intersymbol interference will be there, regardless of how we design transmitter and receiver pulses. Okay? If the gap is equal to 0, that is at rs minus 2w is equal to 0, or that rs is equal to 2w, then we can get intersymbol interference-free transmission. But only So what does zero gap means? It means that these 2 point merges, right? Okay. So what blue curve can produce then a constant function when we add all the pulses together? How should the blue curve look like? Would the triangle work? No, it will not, right? Then it becomes just triangles. It's not constant. So what should it look like? If we add all these pulses together and we want to get a constant. Rectangle sounds good. Okay, so this one will work nicely. Let's see. Okay, because if it does, then by merging these 2 red points here, we see that we get a nice constant, right? From one pulse to the other. Cool. Okay. What can we say about this rectangular pulse in the frequency domain? If we do an inverse Fourier transform on that, what do we get then? We get a sync pulse. Okay. So if one should remember one nice Fourier transform is that if we have a box in one domain, in the time domain, we get a sync in the frequency domain. If we have a box in the frequency domain, we get a sync in the time domain. So they Fourier transform pairs with each other. Okay. So yeah, intersymbol interference free transmission is possible, but only if we design H to be a sync. Okay. And remember that H has to do with the transmitted pulse G and the impulse response of the receiver filter. So maybe it's not super clear how to do that, but it actually turns out to be quite simple. Okay, so trust me on that. Okay, now if the gap is less than 0, meaning that there is some overlap between these 2 boxes here, then intersymbol interference free transmission is still possible. And many of these impulse responses are possible now because we have some freedom. We don't necessarily need to use a box here. We can use something else. And this is the case which is used in practice. Okay. So what have we learned here? Well, we have learned here that if we transmit data, symbols, too quickly, in comparison to the bandwidth, we will have intersymbol interference. Intersymbol interference is bad. We don't want that. Okay, which means that we have to reduce the symbol rate such that it's less than twice the bandwidth. Once we have done that, we still have a chance to eliminate intersymbol interference. However, we still have some work to do because we need to design H such that we fulfill the Nyquist criterion. Okay? We still have to do that. Okay. So before we actually go and do this design, let's see a few more implications of this. Okay, so the practical situation is when RS is related to twice the bandwidth. Okay, so what should the RS be? Should it be equal, greater than, or less than twice the bandwidth? You can look at your notes.
Lower.
Exactly. It should be less than twice the bandwidth. So we have a certain bandwidth, and the more we crank up the symbol rate, sooner or later we'll get into symbol interference. So we have to back off a little bit, okay? And we want to back off as little as possible. But anyways, suppose we have it like this, then W, our bandwidth, can be written, then the bandwidth is of course greater than RS divided by 2. And RS divided by RS is 1 over T, so 1 over 2T is the so RS over 2 is equal to 1 over 2T, right? So we can write then W equal to a little bit more than 1 over 2t. So let's write that as 1 over 1 plus alpha times 1 over 2t, where alpha here is greater than 1. Okay, so alpha tells us how much more than 1 over 2t is W. Okay, so this can be written then as 1 over 2t plus alpha over 2t. Okay. So the first part here is the minimum bandwidth we need. And the blue part here is the excess, or if you want, extra bandwidth which is used. Okay. So typically we have to pick alpha. Alpha has to be greater than 1, but we would like it to make it as small as possible in order to conserve, to make the extra bandwidth that we throw at the problem as small as possible, because we want to conserve bandwidth. Okay. Now, since Rs is equal to 1 over t, we can write Rs divided by W, and then we just use the formula that we had above, and we get that to be 2 over 1 plus alpha. Okay? I just used this formula above and wrote it like this instead. Why do I want to do this? Because an important metric that determines how efficiently we use spectrum is called the spectral efficiency, and that is defined as follows. So spectral efficiency, called nu, is defined as the bit rate divided by the bandwidth used in order to transmit these bits. And the bit rate is related to the symbol rate through log 2 of m times the symbol rate divided by W. And since we know what Rs divided by W is, we know that Rs divided by W is 2 over 1 plus alpha. We can replace that into this equation here and get 2 log 2 of m divided by 1 plus alpha. Okay. All right. So why is this important? Well, the spectral efficiency tells us how many bits per second we can transmit per unit bandwidth. And this is something that we would like to have high. And we see that that depends on two things. It depends on m, which essentially depends on how many bits we transmit per symbol, and it depends on alpha. Okay. So to increase the spectral efficiency, we need to increase m or reduce alpha. But alpha has to be greater or equal to, not 1 here, it should be 0. Sorry about that. Okay. But alpha cannot be less than 0. Okay, so the smallest we can do alpha is 0, and then the only thing we have left is to work on m here. And we will see later on, in order to have that spectral efficiency, to have a lot of m, that is to transmit a lot of bits per symbol, we need a lot of power. Okay. Questions?
What symbol is the first one in the spectral efficiency?
This, okay, so it's new. So how's the pace, by the way? Is it too high, too low, or just right?
It's good.
Is it okay? Okay. Because again, you know, I don't have any particular interest in going through this too fast, right? Because I'm here for you. So I can take it slower, but then of course we cannot cover as much and then you have to read more at home. So just let me know, right, if it's too fast or too slow, and we can adapt. Anyways, let's take 15 minutes.